Everyone. In this video, I'm going to show you guys how I would use Excel to help me do the calculations for the topics that will be on test 2. So I'm going to also kind of review the general ideas from last week's topics as well as this week's topics. So I'll talk about the normal distributions and standard scores for normal distributions, as well as the central limit theorem and confidence intervals. So those are some of the topics I'll be covering in this video. And my goal is to show you guys how to use Excel to do the calculations. So to start off, let's just quickly review the basic idea of normal distributions and what that even means. So a normal distribution is when the histogram of a data set creates this bell-like shape. So the key features of a normal distribution is that the histogram is symmetrical, meaning like if you look at the top half of this histogram, it's symmetrical as or compared to the bottom half. And the center of the histogram is the mean of the data set. So there's lots of different types of data sets that are normally distributed. For example, if you were to look at the heights of adults in America, or maybe the weights of fifth graders, or um, there's lots of different things that are normally distributed. And one of the things about a normal distribution is the 68, 95, and 99.7 rule. So I mentioned earlier that the center of a normally distributed data set is going to be the mean or the average of that data set. And the standard deviation of a data set describes how spread out the histogram is. And the 68, 95, 99.7 rule says that if you go one standard deviation above the mean and one standard deviation below the mean, 68% of your data points will be within that range. So I'm just going to make up numbers here. I don't know if these are totally accurate, but let's say maybe that the average height of adult women is 170. So since it's the average, that means that I could, let me turn on my brush here. That's going to be the mean. So let's say 170 pounds is the average height or the average weight of adult women. And let's say the standard deviation is 10 pounds, just to make it easy. If you add one standard deviation to the mean, that would be 180. If you add two standard deviations to the mean, that would be 190. And three standard deviations would be 200. And then if you subtract those same numbers, you get, or the same standard deviation, you get 160, 150, and 140. Now, again, these are just numbers I made up for the average and standard deviation for the weights of adult women. They're probably not accurate, but I just chose numbers that would work out easily. So what the 68, 95, 99.7 rule says is that 68% of women would weigh between 160 and 180 pounds if my numbers weren't just numbers that I had made up. And 95% of adult women would be between 150 and 190 pounds. And 99.7% of women would be between 140 and 200 pounds. And you can use this to do other calculations. Like, for example, if you wanted to know what percentage of women are more than 180 pounds, you could say, okay, well, all of the data in this histogram is 100% of the data. And if I want to know what percentage is in this part of the histogram, because that's the part that's more than 180, I could say, well, I know that this part of the histogram is 68% by the 68, 95, 99.7 rule. And if I take 100% of the entire histogram and subtract, so I'll do 100% minus the 68%. That's basically giving me the data that's in this part of the histogram and this part because I took away this part here. And since I want to know what this part of the histogram is, I would then divide this number in half because this part is symmetrical to this part over here. And that would give me the percentage of women that are more than 180 pounds. And if I do that calculation, let me actually open up Excel to show you guys how I would do that calculation real quick. So when I'm using Excel, or really when you're doing anything in Excel, you start all of your formulas with an equal sign, and then you type in whatever calculation you want to do. So I want to do 100 minus 68, and then I want to divide that result by 2. So in parentheses, to show that I'm doing this calculation first, I'm going to do 100 minus 68 and then divide by 2. And that tells me that the result would be 16. And in this case, we were talking about percentages because the 100 represented 100% of the adult women. And then the 68% was the part we subtracted out, and so on. And so my answer would be 16% of adult women are over 180 pounds. Again, if my numbers that I made up were accurate, but I'm sure they're not. I just chose numbers that worked nicely. Okay, so that's kind of a general review of the normal distribution idea. Now, a lot of times you're dealing with data points that are not exactly 1 or 2 or 3 standard deviations away from the mean. For example, you might have a woman who is 172 pounds. So she's above the mean, but she's not a full standard deviation above the mean. And the way that we work with data points like that is we calculate what's called the standard score or the z-score. So if we look at your formula sheet for this chapter's test, you can see the standard score or the z-score is calculated by taking the data value, subtracting the mean, and dividing by the standard deviation of the population. So in this example with the women here, our mean is 170. This hypothetical woman that I was talking about is 172. And so you would take that data value, subtract 170, and then divide by the standard deviation. And in this case, the standard deviation that I made up was the number 10, because that was the number that I added and subtracted to fill out this table. And so if I wanted to use Excel to calculate out the z-score for this, I'll just do another calculation here. I would, in parentheses, do 172 minus 170, put that in parentheses, and then I want to divide that by the standard deviation. And that gives me a z-score of 0.2. And what that means is that this data point, or this 172-pound woman, is 0.2 standard deviations above the mean. And sometimes you can get negative values. For example, if you are looking at a woman who was, 154 pounds, if you change that, you get a z-score of negative 1.6. And that makes sense because if she was, I forgot the number I made up, 154 pounds, she would be right here. And you can see that that's more than 1 standard deviation below the mean, but it's not quite 2 standard deviations below the mean. And so this calculation of negative 1.6 is saying that she's 1.6 standard deviations below the mean. Actually, let me use this to show you guys another way that you can also do these calculations. So when I did this, I typed in the numbers into my formula exactly. But another option that you could have done is you could have typed it out with kind of like showing more work. So for example, I would say the value that I'm looking at, so the 154 pounds is the value, the specific value I'm looking for. The mean was 170. The standard deviation was 10. And if I wanted to calculate the z-score, which I've already done up above, but I'm just showing you a different way to do this. You can, instead of typing in the numbers directly, you can use the cells. So, like, I type in my equal sign, and then in parentheses, I would just click on this cell, subtract the mean, and then divide by the standard deviation. And you can see we got the same answer that we did by typing in the numbers directly. But the benefit of using Excel in this way is you can use the same formula for a different problem. So let's say you moved on to a new problem on your test, and this time it was looking at, I don't know, the average trunk length of elephants or something like that. Maybe the average length of an elephant's trunk is, I don't know, 40 inches. Again, I have no idea if this is true or not. And then let's say the standard deviation is 3 inches. And let's say that you're looking at an elephant who has trunk length of 36. In that case, when I change these values, this formula doesn't have to be retyped because it's using the cells that are here. So you can either do it this way or this way, whichever one you think is easiest. But I kind of like doing it the second way because it makes it so that your spreadsheets are more versatile and you can use them from problem to problem. So that's the basic idea of how you do z-scores. So let me do an example of this from section 5.2. So I'm going to go through question 14 on section 5.2. So in this question, it says based on data from a college, scores on a certain test are normally distributed with a mean of 1,528. So in my mean box, I'm going to type in 1,528 and a standard deviation of 318. And then I'm asked several different questions. So on part A, it says find the percentage of scores that are greater than 2005. So the value that I'm looking at is 2005, and that gives me a z-score of 1.5. And that makes sense because if I were to show this on my histogram or my normal curve, the mean was 1,528. The standard deviation was 318. And I'm just going to use Excel here to calculate this part for me. So it doesn't really matter which cells you do it in. You can kind of organize your spreadsheets however you want. But I'm going to say the mean plus 1 standard deviation. This is going to equal this plus the standard deviation. And that tells me that 1 standard deviation above the mean is 1,846. If I do the mean plus 2 standard deviations, so I'm going to do equals the mean plus, you can either do 2 times the standard deviation or you can add the standard deviation twice. Either way, you'll get the same number. But that gives us 2,164. And this z-score that we got of 1.5 makes sense because the value we're looking at is 2005, which is about right here on the number line because it's in between 1,846 and 2,164. And that is reasonable that the z-score is 1.5. Now, this question that we were asked was not how many standard deviations above the mean is 2005. What it said instead is find the percentage of scores that is greater than 2005. So what that's asking us is it's basically saying what percentage of the whole population is less than this value of 2005, which we know is 1.5 standard deviations below the mean. So we could kind of estimate this if we wanted to. Like we definitely know that the percentage should be more than 50% because this mean is halfway. So just this amount of the histogram is 50%. And this amount is still a pretty good chunk. So just eyeballing it, I might say, well, I'm pretty sure it's at least, I don't know, like 80, maybe even 90% because the amount of the histogram that is here is quite a bit smaller than the amount that I'm not looking at, or the amount that's greater than 2005. But the way that we figure out what that percentage is exactly is with percentiles. So the percentile that corresponds to the z-score of 1.5 can be calculated with this formula. So I'm going to type in equals, and then I'm going to do norm.s.dist. That's the formula that's programmed into Excel. And then the first thing that you need to type in to the parentheses is the z-score that you've calculated. And then after that, you type in a 1. I don't exactly know what the 1 means, but that's just part of the formula that is programmed into Excel. And what that tells us is that the amount of the histogram that is less than this value is 93%. And so that's what I would put into this calculation here, or into this box here. And when it's asking for it in percentage form, so I would move the decimal over twice, and that they want me around to 2 decimal places, so it's going to be 93.32%. So 93.32. Oh, did I do that wrong? Hold on. Did I get all my numbers right? Oh, I see what I did wrong. And this is actually, I'm glad I made that mistake. So the question actually asks the percentage of scores that's greater than 2005. And what I found was the percentage of scores that is less than 2005. Because I found this part of the histogram, but the question was actually asking for this part of the histogram. So if they're asking for the percentage that's greater than that, the way that you calculate that is you just say, well, the entire histogram is 100%. And if I subtract this 93% that I found here, that will give me the amount here. So that was my bad for not reading the question well, because I was calculating it as if this had been less than rather than greater than. So we'll call this the greater than percentage. And this is just going to be 100%, which written in decimal form is the number 1, minus the percentage that is less than the value we're looking at. So the correct answer for this one should actually be, I forgot to memorize it. So move the decimal over twice to put it in percentage form, keep 2 decimal places. So it's going to be 6.68%. So 6.68. And now I got that one right. Okay, so that's how you do part A. Then part B gives you a different value. So now instead of looking at the value of 2005, I'm now going to be looking at the value of 1083. So I'll go back over here and I'm going to change this value to be 1083. The mean is still the same because I'm still working with the same mean and the same standard deviation. And the z-score of negative 1.399 makes sense because if we go back to our diagram over here, if you have a value of 1083, that's going to be below the mean. And if I want to, I could do mean minus 1 standard deviation just to check the reasonableness of my z-score. So if I do the mean minus my standard deviation, that tells me that 1210 would be this mark right here. So this is 1210. And if I do the mean minus 2 standard deviations, so equals mean minus standard deviation twice, or you can minus 2 times it. It should give you the same value. That would be 892. And this value that we're working with of 1083 is in between those two. So this value or this z-score makes sense here. And in this problem, we are asked for the percentage of scores that is less than that z-score. And so this time I will be using my percentile percent. Now, technically, actually, the percentile is this value. So this value is in the 8th percentile, is how you would say that. So maybe I'll relabel this to be less than that value. So the percentage that is less than is 8.085, but I'm supposed to round 2 decimal places. So I'll round the 8 up to a 9 because the number after it is a 5. So 8.09% would be my answer there. And then on part C, I'm asked to find the percentage of scores between 1,337 and 1,655. So I have two values that I'm looking here, and I'm trying to find the percentage between them. So if I go back to my diagram here, and it's getting very colorful, so maybe I will clear all of this really quick just to make it a little bit more visually appealing. And then I'll go back and put in these other numbers I calculated. So 1,210 is 1 standard deviation below, and 892 is 2 standard deviations below. So I'm trying to find the percentage of scores between 1,337 and 1,655. So if I look at where those are at on the number line, 1,337 is going to be below the mean, but not full standard deviation below the mean. So I would expect my z-score is going to be negative 0 point something. And then 1,655 is above the mean, but not a full standard deviation above the mean. So what I'm looking for is this, or the percentage of data that is in this range right here. So I could just estimate this and say, well, I know it's got to be less than 68% because the 68, 95, 99.7 rule says if you go a full standard deviation away from the mean, then 68% of the data is between those two numbers. In this case, the 1210 and the 1846. But since the two numbers I'm looking at are less than 1 standard deviation away from the mean, this amount that I've shaded here has got to be less than 68%. But the question is just exactly how much less? So the way that I would do this in Excel is I'm going to find my z-score for my two values. So one of my values is 11337. And I'm just going to copy all of this and make another copy of it so that I can have both of them going at the same time. And I'm going to do my second value here. And if we look at our z-scores, we can see that they're about what we predicted. For the 1337 number, it is a negative z-score, which means it's below the mean. And it's 0.6, which is what we predicted because it's not a full standard deviation below the mean. The z-score for the 1655 is also about what we predicted because it's above the mean, so it's positive, but it's not a full standard deviation above, and so that's why it's 0.399. And then these numbers are telling us the percentages, or the percentage of the data points that are less than and greater than these particular values. So I'm going to use the less than numbers. You could actually do a similar calculation with the greater than numbers, but I'm going to do less than. So this less than value for this one is telling me that this part of the histogram, because this 27% corresponds to the 1337 number, that's telling me that that is 0.274044. That's the percentage that's in this part of the histogram. So it's about 27% in that part I've shaded here. Now, this part right here, the 65, I'll do this in a different color. This is showing me that the amount that's less than 1655, which is right here. So this part of the histogram is about 65%. To be more precise, it's 65.519% of the data. Now, what I want to find is this blue part that I've shaded. And if you look at it, the green part includes all of the blue part and all of the orange part. So if I subtract the orange part from the green part, that will leave me with the blue part. And the way that I would do that in Excel is, and maybe I'll label this as between, is I would take the green percentage, which is the 65, and I'm going to subtract the orange percentage because that orange part is the part that's in the green but isn't part of the blue, which I want to, I only want to find the blue part. And that tells me that the percentage between those two data points of 1337 and 1655 is 38%. And I think the decimal was 0.11. And so that's how you would calculate this. So just to quickly review the formulas, because you can build these spreadsheets, and like I mentioned earlier, if you build them in a way where they are based off of these cells, you can use the formula from problem to problem. However, when you take your test, you will need to start with a blank Excel sheet. You can't use an Excel sheet you've already built. So you need to make sure that you know how to type these formulas in. So the z-score, if we go back to our formulas really quick, the z-score was just found by taking the value minus the population mean divided by the standard deviation. And you can see that right here. And I did it using the cells. And then the less than is by using this norm.s.dist. And that will be on your formula sheet that you can use on your test. And that gives you the area to the left, or the less than percentage of the specific z value that you have here. And then the greater than value is that number subtracted from 1. So you just take the norm.s.dist number and do 100% minus that percentage. So that's how I built my formulas for that particular problem. So one thing to remember is that these types of calculations specifically apply to normal distributions, where the histogram of the data points create this normal curve or this bell-shaped curve. But there are a lot of data sets that do not create histograms like this. And the central limit theorem allows us to calculate z-scores and to work with the z-scores, even if the original data set is not normally distributed. So the idea behind this can be illustrated, well, I think it's easiest to understand it with an example. So my colleague who used to teach this class in person, he did an experiment with his classes where all of his classes, every person in the class, rolled a dice once, and then he also had them roll a dice twice and 4 times. So let's look at the histogram for one die roll. So if I select all of my data and I go to Insert, Histogram, it gives me a histogram that looks like this. But the boxes on my histogram don't particularly make sense, or the bins don't, because dice rolls come in whole numbers. You either get a 1, a 2, a 3, a 4, or so on. So I'm going to adjust my histogram by double-clicking on this, and I'm going to define my bin width to be 1 instead of 1.3. Let's see what that does. Okay, awesome. So what this is saying is actually, let's do number of bins. I want it to be 6 because that only gave me 5. Okay, the legend is a little bit wonky, but basically this corresponds to the dice rolls that were 1s. This shows how many 2s were rolled, 3s, 4s, 5s, and 6s. And if you look at this histogram, it looks kind of similar to what you would expect, because when you roll a dice, it's equally likely to get a 1, a 2, a 3, a 4, a 5, a 6, and so on. And so theoretically, we would expect that this histogram, or all the bars in the histogram, should be equally tall. In this case, it looks like they actually got an oddly small number of 2s in this class. But if they had, had like 1,000 people who had done this experiment instead of only like 133 or however many people were in his classes that semester, the histogram would look more like um, I think it's called a constant distribution. Can't remember the technical name for it, but basically, like all the bars would be the same height. Um, I don't think it's called a constant one, but I can't remember the name right now. And that means that for this particular data set, the normal distribution rules like the 68, 95, 99.7 rule or z-scores or the percentile calculations, those won't apply because the shape of the histogram is not normally shaped. However, we can still calculate the average and the standard deviation if we wanted to. So the mean, or sorry, I should say the mean, not the average. But the reason I said average is because the way you calculate it in Excel is by using the formula average, basically. And then you select your data set. So I'm just going to select all of column A. And when I hit enter, that tells me that the average dice roll was 3.6, which you would expect because if it's equally likely to get a 1, a 2, a 3, a 4, a 5, or a 6, you would expect on average when you add up all the numbers together and divide by the number of dice rolls that it's going to be in between 3 and 4. Theoretically, we would probably think that the mean should be about 3.5, but this experimental mean that they found here is pretty close to that theoretical mean. If I wanted to find the standard deviation of this, if I calculate that, I'm going to do ST-dev, and there's two different ways to calculate standard deviation. One is for a sample, and one is for a population. And in this case, we're going to do it for a sample because this was just one example of rolling a dice. I think it was 133 times. But you could roll, like, have another 133 people roll the dice, and they would get different results. So we're going to use std or stdev.s for the sample standard deviation. And you're pretty much always going to use this because pretty much all of your calculations will involve the sample. And it's really, really hard to actually know the results for an entire population because usually it's not practical to survey the entire population of whatever you're studying. So we'll do the standard deviation of this data set, and that's 1.83, which basically describes how spread out the histogram is. So those are the calculations for finding the mean and the standard deviation of a certain set of data points. So that's the average for this particular data set. And if we wanted to be able to use the z-scores and the 68, 95, 99.7 rule, we would need to be working with a normal distribution instead of this type of distribution that is not normally shaped. And this is where the central limit theorem comes in. So the central limit theorem has to do with looking at sample means instead of individual data points. So in this first experiment that my colleague's class did, they rolled the dice once and they looked at the averages of the individual dice rolls. In another experiment that they did, they rolled the dice 4 times and then they calculated the average for their 4 numbers. So essentially, they were taking a sample of 4 because they were rolling the dice 4 times. And if you find the average of their 4 dice rolls, so I did average and then I selected the 4 cells that I wanted to average. If I copy and paste those all the way down, you can see all of the different averages that the students got. Now, if you look at these values, you'll notice that they're all really close to about 3 or 4, which makes sense because if you roll a dice multiple times and average it, you would expect it to be in between 3 and 4, just like this average that we found here was between 3 and 4 when we rolled it like over 100 times. Now, some of the averages are not because it was a small sample size. Like, for example, if we look at this one, this particular student happened to roll 4 6s in a row. And so when they averaged their 4 results, they got a 6. Or this student rolled a 1 4 times in a row, so their average was a 1. But most of the students had an average that was somewhere between 3 or 4 or close to that. And if we look at the histogram for this, so I'm going to go insert, histogram, go to this. You can see that this histogram is normally distributed. So even though just rolling a dice once creates a non-normally distributed histogram, if you roll a dice multiple times and you find their means or the averages of them, the histogram of the means will be normally distributed. And that's what the central limit theorem is basically saying, is as long as you have a large enough sample size, and technically a sample size of 4 is not very big. If you roll the dice like 20 times each and average that, it would be even more normally distributed. But if you have sufficiently large sample sizes, the distribution of sample means, meaning that you're finding the mean of 4 dice rolls or 20 dice rolls or however many times they roll them to average them, then it's approximately normally distributed, and the mean of the sample means is going to be close to the population mean. So what that means is if I find the mean of sample means, so these are all of the sample means I found, and if I find the average of those, equals average of all of this, then that equals or is close to the mean that you find in the data set of just rolling a single dice. Because that mean was 3.68. This mean is 3.48, and both of those are really close to the theoretical mean of 3.5 that we would expect from rolling a dice. And then the second thing that the central limit theorem says about means is that the standard deviation of the samples means is going to be the standard deviation of the population divided by the square root of the sample size. So what that means here, so we'll say standard deviation of sample means. So I'm going to find the standard deviation of all of these. That is 0.8985. And this number is really, or it should be close to the result that I would get if I took the standard deviation of the individual data points and divided by the square root. So SQRT is the formula for square root. And it's the square root of the sample size. So since we rolled the dice 4 times, I'd put a 4 in there. And you can see this is 0.91 and this is 0.89. And those are pretty close to each other. So that's what the central limit theorem is saying, is that if you get a large sample size, and if I had done more than, if I'd done more than 4 dice here, like if I'd done 20, these two numbers would have been even closer to these ones if I had done a larger sample size. But again, basically, the histogram will be normally distributed even if the original histogram of just rolling it once is not normally distributed. The distribution of sample means will be normally distributed, and the mean will be close to the population mean, and the standard deviation will be the standard deviation of the population divided by the square root of the sample size. And the reason that this is useful is because we can then apply all of the rules about normal distributions to any type of distribution. So to show an application of this, I'm going to go through question 9 from section 5.3. So in this question, it says a certain brand of candies have a mean weight of 0.8588 grams and a standard deviation of 0.0512. A sample of these candies came from a package containing 468 candies, and the package label stated that the net weight is 399.5 grams. And then they do this calculation here where they take the package label claim. So the package of all of the candies should weigh about this. And if you divide it by the number of candies, that's saying that according to the package, each candy should weigh about 0.8536 grams, which is slightly less than the actual mean weight of the candies. So to summarize what we've been given here so far, the population mean, or the actual mean that we have, is given to be 8588. The population standard deviation is 0.0512. And then the size of the sample is 468. And the sample mean is 0.8536. Yeah, that was all of the information that we're given. And the first question we're asked is if one candy is randomly selected, find the probability that it weighs more than this value of the sample mean. So for this one, the sample size is actually 1 because we're only selecting one candy. And we want to find the probability that it weighs more than this sample mean here. So if we go back to our formula sheet and we look at the standardizing z-scores for sample means, the formula is very similar to the z-score we were using before for individual data points. The difference here is instead of taking a data value minus the population mean, we're going to take the sample mean, or in other words, the average of the whole sample we're taking, which for this first question is just a sample size of 1. And we're going to subtract the population mean and then divide by the standard deviation of the sample mean distribution. So instead of dividing by the standard deviation of the population, we're dividing by this, where was it? Standard deviation of the sample mean distribution, which is equal to the population standard deviation divided by the square root of the number of data points. So that's basically what this part is here. So the way I would type that out here, so I'm going to say my z-score, this is going to be equal to, in parentheses, I want to take my sample mean, which is represented by this X bar, subtract my population mean, and then I'm going to divide by, in parentheses, the population standard deviation divided by the square root of the sample size. So that's the way that I would type the formula in. Make sure that you put parentheses around the calculations you want to have done first. So I want these two to be subtracted and these two to be divided, and then divide that result by this one. And so that's why I put parentheses around this part, parentheses around this part, and then divided those two. And that gives me a z-score of negative 0.101. So going back to the question that I'm working on, what this is saying is that selecting a single random candy that is 0.8536 grams is just a teeny bit below the mean, which makes sense because if we look at this number and compare it to the population mean of 0.8588, this number is just slightly smaller than this one. And so that z-score makes sense. And if I want to find the probability that it weighs more than that percentage, that's where I'm going to use my percentile calculation. So remember, the percentile is, or the norm.s.dist calculation will tell me the percentage that is less than this particular z-score. So I'm going to do norm.s.dist, and I'm going to choose that z-score and then put a 1. And that tells me that the likelihood that I would select one candy that is less than this value would be about 45%. But the question asked, find the probability that it weighs more than this amount. So to find the more than calculation, I'm just going to take 100% of my, whoops, I need to do an equal sign, 100% minus the 45% that is less than. And that tells me that about 54% is, or the probability that my single random candy weighs more than this would be 54. So probabilities are usually written in decimal form instead of percentage form. And they said round to 4 decimal places. So I'm going to put 0.5404. And that's the probability that a single candy is going to weigh more than this. Now the question asks, what if you take a sample size of 468? So instead of taking the sample of just one size, we're going to take an entire bag of candy, or 468. And so when I type in the sample size of 468 here, the probability that their mean weight or their average of all of those candies is at least this amount is going to be 98.59%. So almost 99%. Because that's what my calculation gives me there. And if I type that in, 0.098, 599, which rounded up would be 60. Maybe. So that's how you would apply the central limit theorem. And basically what this means is if you randomly select 468 candies, which they said is the size of a candy package, the probability that their mean is at least this amount is 98.6%. And so the company is claiming that the net weight of their candy packages is the 399.5, which is where this number came from, because they averaged it out for each candy. And basically what this 98% is saying is the candy company is providing consumers with the amount they're claiming, because 98% of the time, if you select 468 candies, put them in a bag, it is going to weigh at least the amount that they said. Now, it often will weigh more than that, but nobody's going to complain if they get more candies than what the package claimed. So we would say that it's not exceptionally small, because 98% of the time it is going to be greater than that. So that's how you would do that question. Now, I also want to do a question from section 8.1 that is also based on the central limit theorem. So in this one, it says, assume that newborn girls have birth weights with a mean of 3,046 grams and a standard deviation of 7 and 14 grams. A random sample of 100 newborn girls is obtained, and they have a mean birth weight of 2,996. So notice that that number is smaller than the population mean. And we're asking, what is the probability of randomly selecting another 100 newborn girls and getting a mean birth weight that is either that small number or lower? And does it seem like getting a sample that is that much lower than the average is unusual? Because what these percentages that we're calculating can help us determine is whether or not our sample seems like a reasonable sample from the population, which we'll use to calculate confidence intervals in just a minute. So if I go through this problem, I can use the same calculations I had before that I put into my spreadsheet, which again is one of the advantages of using Excel, is you don't have to use your calculator to recalculate these over and over. You can just change the values. So in this case, the population mean was 3,046. The population standard deviation was 714. The sample size is 100. And the sample mean was 2,996. So that tells us that the z-score is almost a full standard deviation below the actual mean. We knew that it was below because the sample mean is smaller than the population mean, but the z-score tells us exactly how many standard deviations below the mean it is. And then our less than and more than calculation tells us how likely it is that you would get a birth weight lower than 2,966 grams. So I'm going to use this calculation here. And again, probabilities are usually written as decimals, not as percentages. So this means that it's about 24% likely, but we're going to type in that probability as a decimal. So 0.24. 187. So the 7 rounds the 8 up to a 9. We get 19. And then it says since the sample mean lies either less than or more than 2 standard deviations away from the mean. So if we look at our z-score, we can see that this z-score is less than 2 standard deviations away. But if it was like negative 2.7 instead of negative 0.7, then it would be more than 2 standard deviations away from the mean. But in this case, it's less than. And getting a, excuse me, mean birth weight, that is the value they gave us of 2,996 grams or lower, is not particularly unusual. And the reason why we use 2 standard deviations to determine whether or not a sample mean is usual or unusual is because remember the sample means, even if the thing that you are finding the means of or taking the samples of is not normally distributed, the distribution of the means will be normally distributed. And 95% of those means will be within 2 standard deviation of the 2 standard deviations of the actual mean. And so the industry standard is 95% confidence intervals. You can do other confidence intervals, but pretty much any statistical analysis, unless it's like a really unique case, will always have a 95% confidence interval. And so that's why we look at 2 standard deviations as our range of what we consider to be reasonable. And anything outside of that is considered to be unreasonable because less than 5% of the time or less, your sample will be without or outside of the population mean, or outside 2 standard deviations of the population mean. So that's why we use 2 standard deviations. And this is also the reason, if you look at the confidence interval formulas, this is why the number 1.96 shows up in all of these formulas. Because technically, this 95% is a rounded number. It's actually 95.45%. And so by making it just a little bit smaller, because 1.96 is slightly smaller than 2, that's what makes it exactly a 95% confidence interval instead of a 95.54 or 45 confidence interval. So, like I said, it's pretty much always a 95% confidence interval. But if you wanted to do like a 99.7% confidence interval, this number in your formula would be closer to 3. It might not be exactly 3 because, again, this number is slightly rounded, but it would be closer to 3, just like this number is really close to 2. But like I said, it's pretty much always a 95% confidence interval, and all the problems you'll get in this class are 95% confidence intervals. So you can just go ahead and use this number every time. So for my last example, I'm going to go through question 10 on section 8.2 and show you guys how I would use Excel to solve this problem. So the problem says data on 4,600 college graduates shows that the mean time required to graduate with a bachelor's degree is 4.79 years with a standard deviation of 1.27 years. So I'm just going to go ahead and type those in right now. The mean is 4.79. The standard deviation is 1.27. And then it says use a single value. Oh, wait, hold on. Sorry, this is not the population mean. This is the sample mean. So sample mean is, actually delete these because we don't know what those are. And the reason we don't know what those are is because it's not reasonable to actually look at all college graduates and see what the average time is that it takes them to graduate. But it is reasonable to take a sample of 4,600 people and find the sample mean of, or the mean of that particular sample. So that's what 4.79 is. And then we'll put in the sample standard deviation, which is 1.27 years. And then it says use a single value to estimate the mean time required to graduate for all college graduates. Also, find the 95% confidence interval for the mean time required to graduate for all college graduates. So again, we don't know what the actual mean time is required to graduate for all college graduates, but we do know that it should be close to the sample mean because the sample size was really large. And as long as the sample size is really large, the sample mean should be close to the actual population mean. So we can estimate that the population mean is going to be 4.79 years. And then the confidence interval is calculated by adding the error that we can calculate, or sorry, the margin of error, which we can calculate with this formula. So I'm going to go ahead and calculate that. And maybe I'll add a couple rows above here so that I have room for this. So the error is going to equal 1.96 times the sample standard deviation. That's what S is. And then I'm going to divide that, and I'll also put parentheses around this so that it does this first. Technically, multiplication, division can be done in any order with order of operations, but we'll just keep it clean this way. So I'm going to divide that result by the square root of the sample size. And that gives me this error amount. And this error is specifically related to a 95% confidence interval. If you wanted to do a different confidence interval, this number would have to be some other value. Like if it was 99.7% confidence interval, this would be about 3. But since we pretty much always use 95% as our confidence interval, we can just use that number there. So this is the error, and anyway, the way that what we do with this error is we're going to find the lower bound of our confidence interval by taking our sample mean and subtracting the error. And then we can find the upper bound by taking our sample mean and adding the error. So these two numbers are known as our confidence intervals. So I'm going to go ahead and type those in here. And they want me to round to 2 decimal places. So the lower bound is 4.75 years. And the upper bound is 4.83 if I round the 2 up to a 3 because of the 6. So 4.83. So that's, oh, whoops, I didn't mean to move on to the next question. So that's my confidence interval. And what this means is that we have 95% confidence that within this range, uh, the true value of the or the mean time that it takes for all college graduates to graduate will be within that range. So we're not sure that it's within that range because it is possible that maybe our sample that we got just happened to be an outlier, but we're 95% confident that this range contains the true value of the population mean. So that's how I would calculate the error and confidence intervals here. So you don't have to use Excel for all of these calculations. Like if it's easier for you to use your calculator to type out the formulas and that works better for you, you're welcome to do that. But I wanted to make this video to kind of go over how you can use Excel to streamline your calculations. So if you have any questions, let me know, and I hope this was helpful for you.